For our exploration of matter, I've laid out a bunch of matter. Of course, matter is all around us, but here we have a collection of pure substances, elemental substances, mixtures. So let's look at how these things are classified and look at some simple examples of matter. First off, we have, zoom in here, some salts. You can see they all look, a lot of them look like normal table salt, which is in the middle. Sodium chloride is what we call table salt. But other examples of salts could be calcium sulfate. So these are all pure substances. There's one sort of thing in here. It's not really a mixture, but it's not a pure element either, which we'll get to later. But it's very common in the household, and we use them a lot in our labs. We can switch around the elements. Here's the chemical formula, and the common name, Epsom salts, is just magnesium sulfate, also with 7 waters attached to it. And it looks a lot like sodium chloride. And we'll investigate what these mean more later. Baking soda is a salt. This manganese chloride, not magnesium, but manganese chloride is a salt, MnCl2, and it's a little different. It has a cool pink color. Manganese is a hard one to say. It's a transition metal. Mix with that salt, gives it its cool color. Then moving a little bit down the line, we have a couple covalent compounds. Table sugar looks a lot like the salts. Lots of white powders in chemistry, but obviously you know that table sugar has much different properties than table salt. Table sugar, also called sucrose, has a chemical formula C11H22O11, so 11 carbons, 22 hydrogens, and 11 oxygens for each molecule in this jar. Sand is also a covalent compound, 1 silicon and 2 oxygens together, and in bulk you get sand. Here's a more fun one. If you were here, you could smell it. Citronella, you can see it's not just its chemical formula, but its structure is printed on this bottle. And you might be familiar with the smell. It's incorporated into candles as a bug mosquito deterrent a lot of times. And you can see it's a liquid at room temperature. Moving down the line, we have some more covalent compounds. For example, water. This one's labeled in the squirt bottle, deionized water. So that means a lot of the salts that are normally in it have been removed, and other minerals have been removed. Rubbing alcohol is another covalent compound, which we'll talk about more in lab 6, I think it is. Milli-Q water, that just means we have a machine called a Milli-Q that filters the water a lot. So this is pretty close to pure water, which of course is just H2O. 2 hydrogens bonded to an oxygen. And both rubbing alcohol and water, of course, are liquids at room temperature. Now let's move beyond pure substances to mixtures. We have an assortment here. Of course, as I alluded to, things like water can be mixtures. They have minerals in them. So water from the tap has calcium, and this one looks like it has some extra gunk in it. Gross. So you can have a mixture of water. This rubbing alcohol actually is water and rubbing alcohol, so that's a mixture. Gravel is a mixture of different sizes of sand, basically. Rock can be pretty chemically diverse, but you can see here we have sugar, iron and sulfur, pure iron. Whoops. Potting soil. You can see the difference in size between gravel and potting soil. It's more of a mixture. And another one of sulfur, where instead of in solids rocks, it's been ground into a powder. Sulfur is also another chemical you can identify by its smell. Unlike citronella, it's a pure element and not molecules in liquid. So one thing, well, air is also a mixture: nitrogen, oxygen, carbon dioxide, and that can be separated out like we separate out, say, liquid nitrogen from the rest, and this is in the clown car demo. Here I have a magnet, and I can show another way to separate out a mixture. Putting the magnet near most of these substances is not very exciting. You can see I can put it near the water. If you can see that, well, I knocked the bottle, but it's not really doing anything. Actually, water is slightly magnetic. You can Google frog levitation. It's pretty impressive. So some things are magnetic with really strong magnets. This is not a relatively strong magnet. The ones you have in your kits are much stronger. This is just iron, but it's been magnetized, and when you move it near this iron, you can see it attracts. So iron has the property of being ferromagnetic. In fact, the term ferromagnetic comes from the Latin word for iron. I see you have a bad glare there. Let me try to fix that. Okay, so you can use the magnet to separate out. Here the sulfur and iron is finely mixed, and one way you can unmix it is with the magnet. So if I move the magnet around, it will pick up the iron and leave the sulfur behind. It's kind of scuffed from lots of people doing this demo, but let me try to zoom in to give you a better view of how we separated the iron from the sulfur. I guess I could just lift it up. So this mixture is easy to separate by exploiting the property of the iron, which is ferromagnetism in this case. Easily reversible. Next, we're going to look at several examples of pure substances. These are mostly elements, pure elements, and not molecules or compounds. Most of these are metals, but not all of them. So, for example, and some of these are in mole quantities, which I'll talk about too. So we have zinc, and you can find these. This is just organized by its chemical symbol, Zn, which is what's on the periodic table normally. Just a normal looking metal. Copper, we have several forms of. Here it is drawn into a wire. Copper wire is super common and useful. A lot of metals have the property of ductility, which means it can be formed into a wire, or malleability, which means it can be pounded into thin sheets. Here we have some other sheets of copper, and you can see the different colors. It's flexible, and you know the classic copper color. Sometimes it can have a different color, which is an oxide layer on the outside, so it can have a cool red, or even this black, or where is it? Over here somewhere. This kind of, how can I show that? Statue of Liberty green. Statue of Liberty's copper also. Actually, so that would be a copper oxide on top of pure copper. More elements, also metals. Tin. Tin cans are actually typically made out of aluminum these days. This is aluminum foil, which you're probably familiar with. Now, I want to move down to these mole jars. Each one of these jars contains 1 mole of the element inside. So a mole is the number of molecules in 12 grams of carbon. So here's carbon. So this is 6 times 10 to the 23 carbon atoms are inside this jar. And this is carbon black. Carbon in a different form is in pencil lead. So 6 times 10 to the 23. 6, 0, 0, 0, 23 zeros. That's the number of carbon atoms in this jar. So atoms are small, there's a lot of them, and you get a sort of normal amount of stuff. So here's what 1 mole of carbon looks like. Here's what 1 mole of lead looks like. This is super heavy. A mole of lead is like 200 something grams. Let's move iodine over here because that's not a metal, but it looks metallic. This could be a metalloid. Metalloids have properties of metals and nonmetals. Carbon is not a metal, so I'll move it over off to the side. A mole of lead, a mole of zinc, a mole of aluminum, and foil in this case, tin, and copper. Again, but this is 1 mole. And you can look at a periodic table to see how many grams of each subject, of each element, are in 1 mole, because the atoms themselves have different masses based on how many protons and neutrons they have. None of these are reacting to the magnet, but expected this one to. This is iron, Fe is its chemical symbol, and you can see it reacting to the magnet, reacting strongly even to this fairly weak magnet. So a mole of iron, you can read from the periodic table, should weigh 55 grams. So I have here a little scale, or balance, I often call them. See, get it so you can read the numbers. It says 0 now. I have an empty jar that I'll place on it, and to subtract that weight, I'm trying to get rid of the glare, subtract that weight from the other jars, I'm going to press T for tare. So instead of 158.9, once I press T, it'll use that as its 0. So then, when I put like the iron on, it'll give me the weight of just the iron inside, if the bottles were identical. It says 58.77 grams. So yeah, pretty close to 1 mole. Do it with the carbon. That's more closely tied to the actual definition of a mole. 12.95 grams, so pretty close, within a few percent of the accepted value. Okay, so what are some more pure elemental substances? Here we have more copper made into a screen. We have pennies, which you're familiar with. It's actually an alloy. It's copper plated, but there's different metals inside, like zinc. Here we have more sulfur, so this is what 1 mole of sulfur looks like. And its weight, its mass, 34.7. I think it should be closer to 32, but it's close to a mole. Here's iodine again. Now that we're talking about the nonmetals, here's what iodine looks, and it's dissolved in water. See, there's some solid at the bottom. Iodine, and aqueous is what the AQ stands for. Aqueous solution of iodine is used as a disinfectant. And off to the left of the screen you can see this is a block of lead, some more metals in various shapes. This is a copper rod, I think, aluminum in various shapes, just metals. Magnet doesn't do much with those. Let's look at, since we don't have a mole jar for water, we can still look at that. Water is 2 hydrogens and an oxygen. So oxygen is 16 grams per mole, hydrogen is 1 gram per mole, so then water should weigh 18 grams per mole. So I'm going to tear this little weighboat so that the balance reads 0.00, and I'm going to use this squirt bottle filled with DI water to see what 1 mole of water looks like. So I'm going to fill this up until the balance reads 18, should be 0.02 grams to be more precise. 17. Oop. Pretty close. Overshot it a little bit, but that's what 1 mole of water looks like. So there's 6 times 10 to the 23rd and a little more molecules in this weighboat. A mole of air would approximately fill this cardboard box. A mole of air at standard temperature and pressure would take up 22 liters. So 22 standard Nalgene bottles are about, this box is about 22 liters, a little bigger. That's about a mole of air or other gas at room temperature and pressure.